Benita, and just to add something about SCONE, we are hoping to have some in-person meetings also next year in the UK. So this is a recent development. So stay in tune with that. So today we're very happy to have Jennie Traschen from that's a professor at the University of Massachusetts Amherst, and she has done a lot of really important work, mainly on black holes. So we're really pleased to have her today with us, and I'm leaving it to you.
Thank you very much for inviting me and for that kind introduction. I want to add that I love the title SCONE. It brings back possibly my fondest memories of doing part 3 in damped, which I guess was fall of 77 to spring of 78. So I'm going to hide that video, the video stream, so that I can see the full glory of my own screen, which means I can't see your faces. So if people are groaning, I can't see that. If people are smiling, I can't see that. If you have questions, shout it out. All right, so possibly you've already read the title by now, Thermodynamics of Rotating Charge, Cosmological Black Holes and Spin Systems, or How I Came to Love Negative Temperatures. And I think the subtext will hopefully become more clear as I go along. I've had the abstract on the board for a while, so I won't read that to you, but I will point out the punchline. We're going to be comparing KN, Kerr-Newman, de Sitter, so that's charged rotating black holes, to a very simple spin system, non-interacting spins, and get, I think, pretty far for such a simple spin system compared to a more or less complicated gravitational system. And the punchline is going to be, let's see, I have to get my pointer. Let's see, laser pointer pen. No, that wasn't what I wanted. I'm so sorry. Laser. I'll try a laser pointer. Okay, at least that's a little blob. The punchline is down here in the bottom corner of the slide, is we're going to be comparing, on the one hand, rotating black holes, and on the other hand, the simple spin system. And what we'll end up with is an identification, for example, of the number and of non-interacting spins with the parameters of the the black hole. And what we find is that this interpolates from very small black holes to a dependence that goes basically 1 over lambda with some g's put in, g's and h bars to make the dimensions right. And on the left-hand side there, that's the most obvious thing that it's dimensionally, it's the one thing one has is if you're talking about just de Sitter. So for a very small black hole, you recover that answer. But when you add more parameters to your black hole, and in particular charge and rotation, then we'll see that the dependence of the number of degrees of freedom in the spin system changes. And on the right-hand side, I have different people that I've worked with on this work. And I do want to point out that a lot of these were graduate students when they did this. Chakrabarty, Etheridge, Hugh Chu, myself. The first paper I'm going to talk about, Jack Dinsmore, was actually a high school student when he started the work. That was also done with Patrick Draper, who is faculty, David Castor, my colleague, also faculty, and 2 other undergraduates at UMass, James McNerney, Gautam Satyastranjan, who's now a postdoc at IAS. So it's been fun working with all these different people. And I also have up here a partial list of other people, people that I haven't been collaborating with on this work that have worked in the same kind of topics. All right, first an intro before we get to the outline. So basically, the story starts with studying Schwarzschild de Sitter, that is to say, no rotation, no charge. And one day, the student, who was actually a high school student at the time, came to my office and showed me these plots that plotted the area of a black hole versus the temperature or surface gravity of the black hole. So again, this is for Schwarzschild, but with a cosmological constant. So the area versus temperature curve looks different than it does without with lambda equal to 0. And what this plot highlights is that the area interpolates between a minimum value and a maximum value. I'm just looking at, and if you take the slope of that, I mean, there's something that doesn't, the first slide, I see something that doesn't look right. Oh, I'm sorry. The thing that's not right is the verbiage. It's the area of a black hole. It's not the area of the black hole. I missed that, correcting that on my slides. This is the total area for the black hole and the cosmological horizon. So let me pause and ask if anybody has any questions. I had noticed that error and then I didn't fix it, and now I'm paying the price. The reason why this area interpolates between a non-zero minimum and a non-zero maximum is because it's the area of the sum of the two horizons. The largest area is as the temperature gets, the black hole temperature gets big, that's because it's dominated by the cosmological area, and the smallest area is at the other limit when the cosmological and black hole horizons merge. Did anybody have a question now, since I started with an error?
That's clear.
Okay, all right. So if you take the derivative of this, then you notice that there's a peak in the derivative dA d temperature. And I haven't shown it here, but if you look at the mass of the system, the mass also shows a similar peak. And if we're taking the derivative mass, d mass, d temperature, then we call that the specific heat. All right. So that looks, adding lambda changes the picture significantly. So I asked around to my condensed matter colleagues and said, like, is there some condensed matter system? So, thermodynamics I can be familiar with that looks like those plots. And the answer is yes. And indeed, it's a very simple system. I was pointed to a two-state statistical system, for example, a paramagnet. And if you...
Jenny, there's a question
Okay.
from Sayan
Actually, sure. Maybe just a small question because you passed it up. So when you said that the mass also has a peak, what do you mean by mass for the de Sitter black hole? Because the ADM mass would diverge, right? I mean, it doesn't satisfy the asymptotic condition because there is a lambda
so
square, right?
Defining, no, so I guess I would disagree with you. So that is something that I've done a reasonable amount of work on, and one can take the Hamiltonian or ADM framework and fix different boundary conditions than asymptotically flat. So say asymptotically de Sitter, and then consider spacetimes that fall off at appropriate rates that you have to figure out so that the integrals can converge. And using the symmetries of the spacetime, likewise define ADM charges. So I think I'm not going to say anything more about that procedure. It is more complicated for asymptotically de Sitter, you have the killing vectors. For asymptotically Robertson-Walker, you can also do that. It's a bit more complicated, or one has to break new ground because you don't have the same symmetries in a general Robinson-Walker. Okay, but if I go that route, I'm never going to get it far.
Sure. Okay, thank you, ma'am.
Okay, so in the canonical picture, it's easy to understand why you have this. In this system, you have n spins, and n is fixed. And this only two states, so they don't have to be spins, just two states. And the different members can occupy these two levels with energy 1 and energy 2. In the canonical picture, if the ambient temperature is much less than the energy gap between the two states, almost all the objects are in the lower energy state. And lowering temperature further has no more effect on the distribution because everybody's already in the lower state. And likewise, if the temperature is much greater than the gap, the two levels are equally populated, and raising the temperature further has no effect. So you can see why the entropy versus temperature curve has that shape. One can also analyze that in the microcanonical system, and I've drawn the picture here. We see something interesting when we go from the canonical to the microcanonical. Here I've plotted the number, the entropy for, again, fixed number of spins versus the energy. And you can see that there's two places where the entropy is minimum and a maximum place in between. If you take the derivative of that curve, you get the picture of the temperature that I show on the right-hand side. I'm not going to say anything more about these pictures right now because I'm going to come back to them and talk about the physics in a little bit more detail. But this is a framework to have in the back of your mind. I want you to have these pictures in the back of your mind because there was some earlier work that I had done with two undergraduates at UMass, McNerney and Satish Chandran, which is long enough ago that I'd kind of forgotten about it. And what we did was to take a look at the parameter space for rotating black holes with lambda. And the parameter space is very rich. We'll come back to that in a minute. But one of the curves in one portion of the parameter space, area versus mass, looks like this. The area goes up, there's a maximum, it goes down. So that picture is supposed to look similar to you as the entropy versus energy for the spin system. So I pose the question, does the similarity between black holes and lambda, the picture on the top, and the similarity of that with the spin system have any physical meaning? That's the question we're going to address in this talk. And of course, I'm claiming the answer is yes. Now, this outline got way too long, and I'm just going to mention the first couple of steps. I'm going to start by talking about rotating charged de Sitter black holes, and in particular, talk about a symmetry of the total area, where by total area, I mean the sum of the black hole and cosmological horizon areas. And then we'll switch gears and very briefly review the thermodynamics of a two-state end spin system. And then we're going to do some swapping, comparing the black holes and the spins. And like we just saw, there's a straightforward comparison, a matching between the area of black holes and the entropy for the spins. But the temperatures don't obviously match. So that'll prompt us to go back to the gravitational system and come up with it. It's not really a new concept. The definition has appeared in the literature. Perhaps the way I'm going to present it is somewhat new. That I'll call the system surface gravity. And that's going to complete a nice analogy between these. I'll possibly get to talking about constrained systems of spins, which will allow making inferring a relation between the black hole parameters and the different parameters of the spin system over a larger portion of the black hole parameter space. Okay, so I'm not going to say anything about this slide. I just put it in. This is the metric for rotating charged black holes with positive lambda. Lambda here is denoted by, it comes in through the length scale L squared. I just put this metric on the board, or not on the board, put this metric up because this is GR talk, and to remind you that there is a metric. This spacetime has 3 horizons. We're going to be focusing on 2 of them. There's a function in the metric, which is called delta here. And as the more familiar case, perhaps, of Schwarzschild, these horizons occur when this function, which I haven't written down. Oh, yes, I have. That function's there. That the zeros of that function. And then the surface gravity at that particular horizon has to do with the derivative of that function. So that's just to let you know that there's actually honest definitions, because mostly what I'm going to be doing here on in is to show pictures and make statements. Right. So as mentioned, there's 3 horizons, an inner cosmological, black hole, cosmological, and inner. The inner horizon is due to the presence of some angular momentum and or charge or both. Having the inner horizon is important for this talk because that provides a lower mass limit where the mass is non-zero. So rephrasing that, there's 2 horizon merging limits where the temperature or the surface gravity of the black hole is well behaved. It goes to 0. So when the inner horizon approaches the black hole horizon, the surface gravity goes to 0. That's the situation of the minimum mass black hole, which is non-zero, and actually the total maximum area for the sum of the areas of the cosmological and black hole horizon. So if you like to consult this little picture, this picture goes along with these statements. Here's the black hole horizon. Here's the cosmological horizon. Both horizons are endowed with an area and a surface gravity. And I've tried to sketch in the fact that they're rotating. If we put ourselves in this middle region between the 2 horizons, then these arrows indicate that things are leaving the middle region. So things go into the black hole and things go outward through the cosmological horizon. Okay, so a very important difference with having a charge and angular momentum is that we have this nice limit, the small mass black hole, where the surface gravity goes nicely to 0 rather than infinity. And one of the problems with matching just the Schwarzschild-de Sitter spacetime to a thermodynamic system is you're not going to see the black hole instability in a nicely behaved thermodynamic system. So it did occur to me that even though rotating black holes with lambda are more complicated than non-rotating ones in some ways, in other ways, like thermodynamics is much simpler, it's better behaved, and one does not have to deal with the black hole instability. So as I said, there's 2 limits in which the black hole temperature goes to 0, and those are the 2 different ways horizons can coincide. The other way is when the black hole horizon merges with the cosmological horizon, called the Nerai limit, and that's a situation of maximum mass and minimum total area. A really important distinction between this system and black holes without with 0 or negative lambda is that the mass is bounded between a min and a max, and the total area is bounded between mins and maxes. And you can see that that's important for connecting with a thermodynamic system of spins where you have n fixed spins. Then the total energy is going to be bounded, the total entropy is going to be bounded. So by moving to a black hole situation where we have these 2 horizons, cosmological and black hole, we're moving to a situation where the mass and entropies are bounded. Okay, as I mentioned, there's 2 surface gravities, and I'm going to try to say surface gravity when I'm talking about the black holes, and temperature when I'm talking about the spins, just to differentiate. But anyways, here's the well-known relationship between temperatures and surface gravities. Well, actually, maybe this other one is not so well known. I've decided to call the temperature the positive quantity that's minus the absolute value of the cosmological surface gravity. So perhaps I didn't emphasize the temperatures of surface gravities. I can't get out of that habit. There's 2 different surface gravities. The black hole surface gravity is always positive. On the other hand, the cosmological surface gravity is always negative. And the 2 surface gravities both go to 0 when the black hole and cosmological horizons coincide. On this plot was from this paper, we were dealing with the magnitude of the cosmological surface gravity. So it's our temperatures or the magnitude that's plotted here. And really, I'm just showing this plot to illustrate that the parameter space of the rotating black holes with lambda is very rich. And there's different kinds of behavior. So this, on the left-hand side, is the black hole temperature and cosmological temperature in the dotted line for in one portion of the parameter space. On the right-hand side is the black hole temperature and cosmological temperature in a different portion of the parameter space. And I've noted here that in some parts of the parameter space, as illustrated here, the magnitudes of the surface gravities can be equal. So in terms of temperatures, TB equals TC, or in terms of surface gravities, this kappa B equals minus the surface gravity of the cosmological horizon. And equal temperature places, of course, are always interesting for when you might have two different thermodynamics or two things at different temperatures combined in a thermodynamic system. All right, what I'd like to get to next is a symmetry of the total area for in these rotating lambda black holes. So to see what's going on with the geometry of the rotating black holes, I mean, it's nice we have the metric, and the metric is a 4-parameter metric. Have I listed them here? I haven't listed them in this slide. The mass, angular momentum per unit mass, charge, and lambda. And so that's nice. You have an analytic solution for the metric, but there's a lot of other geometrical quantities one wants to know about, for example, the surface gravities and the horizon radii. So there's more than 4 things that one would like to know about. And unfortunately, the algebraic formulas for them are all intertwined. So you kind of have a mess. And it's hard to see how things relate to each other. It's hard to draw pictures. So one of the things that I did with James and Gautam was to trade the parameter m for a new parameter called x. And this parameter was chosen because we could actually write formula for all the things that you might want to write, the horizon radii, the surface gravities, the mass, the areas, as functions of these 4 parameters. So keeping L as for cosmological constant, A, angular momentum per unit mass, Q, charge, and instead of M, capital X. And by functions, I mean that you can have your radius, your horizon radius on one side, and it's equal to something on the other side. So then at least you can either sketch a plot or you can plot one using some numerical means, which you can't do in terms of the original parameters. So the definition of X is quite simple. It's the product of the 2 horizon radii. And what I'd like to showcase here is that writing the total area, sum of the black hole plus cosmological area, in terms of capital X, we have this very nice, simple formula. A twiddle squared sums the angular momentum and the charge. L is the cosmological constant. Gamma you should think of as a constant. It depends upon 1 plus a squared over L squared. So the thing to really focus on here, say if you're fixing angular momentum, charge, and lambda, the thing to focus on is the dependence on capital X. Now it turns out that this new parameter X has a nice property that it's monotonic with the mass. X increases with M, so that you can at least think of increasing X is increasing the mass. Right. One thing that jumps out at you with this formula is that there's a symmetry of the total area, that the total area of a spacetime with parameter X, or secretly mass, is equal to the total area of spacetime with 1 over X. Well, not really 1 over X. You have to get the dimensions right. So it's a squared L squared over X. Okay, so I put the formula for the area here, and again, the symmetry. And if you, well, there's 2 different ways to think of it. Why don't we go to the lower corner here? This returns to a plot I had shown in the introductory section, which gives the total area as a function of X. And you can see the area has a minimum, actually the same value of minimum at 2 different values of X, has a maximum in between. And what this means in terms of geometry is suppose you draw a horizontal line across this plot. That horizontal line intersects the area curve in two places. So that is to say, two distinct values of x. That means for the chosen values of angular momentum and charge, each value of x in the allowed range has a partner spacetime or dual black hole spacetime in which they're both black holes. They're different spacetimes because they have different x or different mass, but the total area is the same. Now, I've emphasized here that you have to be picking values of x that are in the black hole parameter space. So one of the side calculations you have to do is figure out what values of angular momentum, charge, and cosmological constant and x go together to be an actual black hole. But I won't talk about that. I won't talk about that process now. But this nice symmetrical, or what we call totally dual area versus mass, area versus x curve, is for a portion of the black hole parameter space, not for all the black holes. And indeed, in the lower right-hand case, at the corner of the slide, I've sketched how the total area varies with x if you move around in the black hole parameter space. So for some of the curves, like this purple curve, then if you're at a larger value of the mass, then the larger mass spacetime has a partner, a dual. But there are other spacetimes down here, other values that don't have a partner, and so on. So as you move in the black hole parameter space, you can move away from this nice totally dual curve. So it's a rich system. And finally, in the upper right-hand corner is a picture of two embedding diagrams for the two horizons, the black hole and cosmological horizons of double S of spacetime and its dual spacetime. So the two red curves correspond to one value of x, and then the two dotted blue curves are the horizons for a different value of x. So that gives you some idea about how the horizon geometries change, but the areas are the same, believe it or not. Okay, we're going to move to spins. So let me pause and just see if there are any questions. All right. Very short, either preview or review of a very simple spin system. We're going to consider n non-interacting spins in a magnetic field B. And the role of the magnetic field is to change the energy of the spin, that's spin up or spin down. And I'm using the nomenclature that the higher energy state is spin down. So we can divide the total n into the number down and the number up. And that allows you to write the energy, which is typically and conveniently written in terms of the fraction n minus over n. And so n minus is down, but it's the higher energy. Okay. And this fraction, being a fraction, it normalizes so that it goes between 0 and 1. So the total energy is bounded for this system. There's only n spins. And the thing that's very nice or interesting about this system is that you compute the entropy by counting the number of states. I want to say how many states are there with my favorite value of n minus. And then the entropy is the log of those number of states. And the entropy turns out to have this simple form. But here I've drawn a picture of it. The nice thing about the interesting thing about the entropy is that there's two different configurations of spins where the entropy, it has its minimal value, in this case 0, and then the curve goes up and then down in between. So there's one configuration with the maximal entropy. So the one at the left, the lower energy curve, is when all the spins have lower energy, so they're as parallel to the field or up. The higher energy curve is when all the spins are anti-parallel or all down. So both of those configurations, they differ in energy, but there's only one way to get each of those configurations. So they have the same value of the entropy, and it's 0. This curve has a symmetry that it does because the counting doesn't care whether something's called up or called down. So if you do the counting and say you're counting the number of states with up, that's the same as switching your names and saying, oh, I want to count 17 down. So that's what gives this entropy its symmetry. It does, for the counting of states, it doesn't matter if that number 17 or 1700 or 17,000 is called all up or called all down. So that symmetry of the entropy gives the curve its shape, and the fact that the energy actually does care whether they're up or down. Now, there's another thing that's really nice about the curve is that you can see that the slope of the curve on one side, because of that symmetry, the curve goes up and then goes down. The slope on one side is positive and the slope on the other side is negative. And that's cool from a physics point of view, because we know that the slope of entropy versus energy has to do with the temperature, or actually 1 over the temperature. So it's straightforward to compute the derivative ds dE, and I've drawn a picture of it here. My parameter lambda going to the right is increasing energy. And so this positive temperature corresponds to the positive slope on the plot. And then this negative temperature, the fact that you have a negative temperature, nothing spooky there, that just corresponds to the fact that one side of the entropy versus energy curve has a negative slope. So from the point of view of the microcanonical ensemble, if you have a system with the kind of symmetry that imposes the symmetry for the entropy curve, as with these spins, it's very natural that you would have negative temperature. All right. So now we're remembering that the entropy versus energy curve for the spins looks a lot like the area versus mass, or area versus X curve for rotating black holes. But these temperature curves don't match at all. They just look different. But then you say, oh, but they couldn't really match, because look at, this is the temperature, or why should I try to match them? This is the temperature for the whole system of spins. And here I'm talking about 2 different surface gravities for subsystems within the black hole spacetime. So what we're going to do now is to try to find an analog of a system surface gravity that combines the whole system, describes something about the system of the black hole and cosmological horizon, so then we can compare the system surface gravity to the temperature for the spins. All right. So the way to do this is to use the first laws. And I've put the first, there's 2 first laws that are of interest here. You have 2 horizons, black hole and cosmological. And so in the construction for the first law, you can take your connect infinity with the black hole horizon, or connect infinity with the cosmological horizon. And those give you 2 different first laws. And here are the first laws again. And I remind you that kappa B, surface gravity black hole, is positive, kappa C is negative. Now, there's too much algebra on these slides well, it's actually just the results of the algebra. But the point is that we can take linear combinations of these first laws. And in particular, I've done 2 different kinds of linear combinations. First, let us fix J, Q, and lambda. So that makes most of those terms in the first laws 0, and then take appropriate linear combinations. I left off a delta there. Okay. I want to find the linear combination so that I'm relating the change in the mass to the change in the total area. So that means I have to add the 2 black hole and cosmological areas. And if you force the total area to be one of your, to come out on the right-hand side, that tells you what the coefficient is relating delta M to delta area. And it's a product of the surface gravities over their sum. I'll just mention that if you fix little a, the angular momentum per unit mass, charge in lambda, then that gives you a different what do we call it? Oh, well, this parameter, I'm just going to call it, it's a system surface gravity. This gives you a different multiplier relating the mass to the change in the area, the total area. So depending upon what you hold fixed, this multiplier, which I'm going to call the system surface gravity, has a different form. Okay. In either case, we can think of the relationship that the change in the mass is the surface gravity for the system times the change in the total area with the happy factor of 8 pi. And then kappa system has different forms depending upon what you want to hold fixed. Now, 2 comments here. This kappa system can be positive or negative. And interestingly, at fixed J, for example, because that's a simpler expression. So if we go to fixed angular momentum, we see that this kappa system goes to infinity when this denominator goes to 0. And that is to say when kappa B equals minus kappa C, or in terms of the magnitudes, the equal temperature place. So that's interesting because the spin system has this place where the temperature curve goes to infinity. And we'll compare in a moment. All right. In order to make the symmetry of the total area look a little more like the spin symmetry, I've switched to a new parameter y, which is basically x is e to the y. And that makes the area, the symmetry of the total area, that the area at a value y is equal to the total area at minus y, which is more like lambda goes to 1 minus lambda. It's just a shift symmetry rather than x goes to 1 over x. Okay. So plotting the system surface gravity as a function of y, remember y is essentially x, which is essentially the mass, and they've just shifted and mangled a little bit, that the system surface gravity now is positive in one part of for one range of y, is negative for another range of y, and goes to infinity in between. So now we can actually make a more robust comparison with the rotating black holes with lambda and the microcanonical description of the spins. Here is an area curve. On the right-hand side is variously x, y, or m. They all increase monotonically with each other. This is the area curve for the totally dual black holes. And that qualitatively is similar to this entropy versus energy curve in the spin system. And now our system surface gravity is qualitatively similar to how the temperature of the spin system behaves. Again, the negative branch of the spin system just comes in because the entropy curve has positive slope and negative slope. And the fact that the system surface gravity can be negative, it's not always negative, but the fact that it can be negative for some of the black hole parameter space, some values of the mass, that comes because the cosmological surface gravity is negative. So it depends in the definition of the system surface gravity, there's a competition for sign depending upon who wins, the black hole or the cosmological surface gravities. Now, you'll notice that there's qualitative agreement between the different temperature curves in terms of the positive side, the negative side, going to infinity in between. Of course, the curves go to infinity because there's a maximum of the entropy. There is this offset on the for the system surface gravity for the black holes. The kappa system does not go to 0 at the large mass end, whereas for the spins it does. So not everything is agreeing. Okay, punchline number 1. And then I'll pause for questions again. So comparing those 2 plots to each other, so I say use qualitative agreement between the area, total area and the entropy, system surface gravity and temperature for this part of the black hole parameter space. Since the zeros of the area does not match the 0 of the entropy, which are 0. What we're matching here is a difference between the maximum of the area and the minimum of the area. And just equating those two things gives the following relationship, tells you the number of spins has this nice little formula. It's related to a squared plus q squared square root, and goes like the square root of lambda in the denominator. And I remind you that this is for the totally dual black holes. Here is a kind of a colored picture of the black hole parameter space showing q on one axis, a squared on, I'm sorry, that's q squared and a squared on the other axis. The different colors codings corresponds to different qualitative behaviors of the area curve, and the totally dual ones, which we're talking about claiming for in this correspondence between n and the black hole parameters, is this curve that I've tried to highlight there. All right, I'm going to change my position a bit and ask for questions. All right. Now, we would like to be able to compare black holes in the rest of this parameter space, not just confined to this one curve in the parameter space. And to do that, what we did was to look at a constrained subsystems of spins. Okay, so again, the motivation here is to be able to obtain a correspondence between the spin parameters and the black hole parameters in a larger portion of the black hole space. Okay, so the spin system comes to us in terms of a total description, whereas the black hole system naturally comes to us in terms of subsystems, black hole and cosmological. So what we want to do is rethink the spins and say, well, how can we get two separate temperatures that would correspond to the two separate surface gravities? So the approach that we used was to divide all the spins into two subsystems called B and C. And that is to say that all the spins are written as a sum, n sub the B's plus the C's, and that the sum of those two things are fixed. But the ratio of NB to NC can vary. And then likewise, the number of spins down, the higher energy ones, are those down in the B's plus those down in the C's. And you can again define a fractional number down for each of the B's and C's, and I call that lambda. Lambda sub B, lambda sub C. So now the total entropy gets a contribution from the B's, weighted by the number of B's, and a contribution from the C's, weighted by the number of C's. But now we want to start putting some constraints on these subsystems to try to get it to match the black hole systems. So the strategy is to take lambda B less than a half, where that's the range where the temperature function for the spins, the temperature function that goes with this S, is positive, and to take lambda C greater than a half, which gives negative temperature for the spins. Okay, so here's one constraint on our subsystems: lambda B less than a half, lambda C greater than a half. Now, each of these subsystems has some energy, and the total energy for the spins just adds. And the energies, really, you can swap the energy of a subsystem for its lambda. So fixing the lambdas for getting the temperature right tells you what the energy is in that subsystem. Now, this kind of innocuous statement is a little interesting, because in the black hole case, we don't have a division of the total mass the total mass cannot be written as a sum of the mass from the black hole and a mass from the cosmological horizon, which is an interesting difference. Okay, however, what we can do is that we have two first laws that relates the changes in the mass to changes in the area of the black hole, and a different statement that relates to change in the mass to the change in the area of the cosmological horizon. Notice that this is the same delta M for each of these two versions of the first law, where I've put all the variations equal to 0. So we're just relating delta M to the changes in the areas. That it's the same delta M, not two different ones. So that tells us another constraint of all the possible ways that we could divide up the spin systems or describe different subsystems, is that we have to choose subsystems in such a way that the change in the energy of the B's is equal to the change in the energies of the C's, for example, as we move along the temperature curve. Okay, so that is to say, we have to impose for the spins, the change in the energy of the B, of course, is its temperature, delta SB, and likewise for the C spins, but that delta E, but that these two energy changes for the B's and the C spins are equal. So rewriting these two relations, again, the algebra is the same as what we worked with in for the black hole first laws. That tells us that the change in the energy of the B's plus the C's is some factor which I called the system temperature times the change in the total entropy, that is to say, the change in the entropies of the B's plus the change in the entropies of the C's. That was a lot to say. And the system temperature has the same form as the system gravity because it's the same algebra. You just change the names of things. All right. So to summarize, for the constrained spin systems, we want to take lambda of the B's less than 1/2, lambdas of the C's greater than 1/2, and then we have this constrained first laws that the spin systems operate by. Now I'm showing you a picture of another part of the black hole phase space. So this is going back to black holes, so we can have a picture in mind of what we want to match. This is the area versus y, which we call y is essentially x, which is essentially the mass. So increasing mass on the horizontal axis. On the right-hand side here is the totally dual area case. Again, you can see this area curve is symmetrical. And then on the left-hand side, this is from a different part of the black hole parameter space, a part that allows us to get to small mass black holes. And you can see some of the black holes here have dual partners, but if you go to these higher mass black holes within this region of the parameter space, there's no dual space-time. Actually doing the construction of the criterion for the spins, so the subsystem, is a bit weedy. And given the time, I think I'm not going to go into the details of that. But the idea is to try to match qualitatively, going from this picture of a symmetrical entropy curve to this not symmetrical entropy curve. How are they differ? Well, in the left-hand, the less symmetrical one, the area starts at a higher value, or the entropy starts at a higher value at the low mass end, and then goes to a lower value at the low mass end. So that's one difference, where on the right-hand side, it's the same value. And the actual magnitude of the total area on the left-hand side is bigger than the maximum, the actual value of the maximum of the area. So both of these curves have maxima in the entropy or area, but one is higher on the left-hand side. It's a bigger entropy than on the right-hand side. So that's what I've said down here, is we want to match the subsystems at the two ends, the low mass, high mass end, and also at the middle, the maximum end. So I'm going to skip the details and skip over to the punchline. And so here's some, again, description of what we do. Matching the temperatures at large E, small e, and maximal S show, we argue that that can match the constrained constrained spin systems can match the small dual black holes in the part of the black hole parameter space that includes very small black holes. We don't want to go down to zero mass, zero angular momentum, zero A, because we want to stay away from the black hole instability. So that we're considering cases where we can let the mass get very small, but non-zero. And one way of seeing this correspondence is to look at the maximal entropy configuration and identify what the kind of ionization or the fraction of spins down is in the B's and the C's. So equilibrium refers to maximal entropy or equal temperature. Okay. And then we argue in the paper that the spin entropy changes qualitatively in the same ways as the black hole entropy does. Long story. The punchline is that, ooh, look at this is 1, 2, 3, and 2 again. Comparing the area, the total area of black holes and the total entropy, the sum of the B's and the C's, gives a relationship for the very small end that's where the number of spins is 1 over lambda, and that interpolates up to the situation that we had started by looking at for the totally dual black holes, in which case the areas are parametrically comparable. We're in this, what I'm calling small areas. The black hole area is much less than the cosmological area. So this slide is really the punchline for the results. Skipping over all the details of matching. I'll save this slide if anybody asks me what the relationship is between M, X, or Y and the spin system. Okay. So to conclude, we've tried to address the question of how does the horizon picture, where you have us in the middle, that's not US, that's us, we're between the two horizons, and this region in the middle is characterized by stuff goes out through the cosmological horizon or stuff goes out through the black hole horizon. The commonalities of that system, which are summed up in this area curve and the system temperature, how does that emphasize that there are similarities between the thermodynamics of the black holes and spins, and use those similarities to actually deduce a correspondence between the n of the spins and the parameters of the black hole. So this is my last slide. There's lots of questions which we didn't answer in this work. And most interesting perhaps is in blue, like, so what do these ends correspond to? The ends, and if you're breaking them into subsystems, what are the NBs and what are the NCs? And what is the difference between up and down in the spin system? What does that correspond to in the black hole system? But I think that I'll leave those as open questions. And I see it's just about noon my time, or 5 o'clock your time, I guess, or 1700 your time. Okay. So thank you for joining me.
Thank you very much. You have some questions. Yeah, Professor Force.
Yes. I'd like to ask a question about physical medium negative temperatures in both of these systems. As we understand, with the spin system, negative temperature corresponds to a population inversion, and and in a sense, any negative temperature is hotter than any positive temperature because a system with a population inversion will tend to transfer energy to any system with a positive temperature. Now I wonder if there's something analogous in the black hole case. Can we take a negative temperature black hole system and say anything about which way heat would flow if we were in whatever sense we have to, in some sense, put it in thermal contact with a positive temperature system?
Yeah, well, I mean, those are all these questions that I'm asking for future directions. So I'm
Okay.
happy for suggestions, the audience. But let me still make a few comments. Um, I I think that I've personally found it more useful to think about all the de Sitter systems, whether with spin or without spin, in the microcanonical picture as opposed to the canonical picture. So in the canonical picture, one has this idea that there's a system and then there's some heat bath. And indeed, that's the role of the parameter T, that this external heat bath is imposing a temperature, fixing a temperature. And indeed, to my small knowledge, T in canonical picture is always kept as positive, although maybe, well, whereas in the microcanonical picture, you don't have an outside. And I think that is the case in these black hole systems, that there's not an outside. We don't have a black hole to manipulate and put it in the fabled box, where the box has some fixed temperature. So I personally find the microcanonical description more compelling in the sense that it doesn't pretend that there's an outside in which you can fix certain things. And then, as I tried to argue, the negative temperature is just an unnatural part of the microcanonical description. I mean, and of course, there's an instability there. This microcanonical description of the spins doesn't tell you what happens, right? The dynamics are not there. But you can go on to investigate that if you add some kind of perturbation, when the system's in the negative temperature side of the curve, that, yeah, it's probably going to evolve up to the maximal entropy state, and that I wouldn't go, for me, I'm not going so far as to claim the same thing for the black holes, but I think one has to, of course, obviously it's interesting, I mean, that's it. Maybe the Hawking radiation does take you along that curve, and that might be what you're getting at.
Okay. Well, thank you.
Yeah.
More questions?
Actually, I have a question that's maybe related to that. I was wondering how the system changes if we had Hawking radiation, and if you think the analogy could be extended in that case.
Yeah, well, I mean, I think that's probably what you would argue is that on the negative temperature side of the curve, that you would the Hawking radiation probably you might probably or where you I'm stumbling. I don't know how much certainty to put on that, but Hawking radiation probably takes you along this curve. In going from the maximal total entropy state, if you want to get to the smallest mass black hole, then the argument becomes a little bit different. The way that we usually think about going down this part of the curve is because we're thinking about the black hole. I mean, so maybe I'll leave this as a question for the audience. So here's the black hole temperature. And we think about going down to smaller mass by radiating down the black hole temperature. So maybe that's what's going on with also looking at the total system temperature, okay, that you're going down to smaller mass. But so I got lost in terms of the entropy. The maximal, well, yeah, this is what I was trying to say. The maximal total entropy is not at the minimal mass black hole. Okay, so one has to, so I don't know which argument you want to use. If you're going for the maximal total entropy or total area, then this configuration, a kind of a medium, intermediate mass, has the maximal entropy. On the other hand, that's not where we think that black hole evaporation is going to take us, down there, you know. So I'm not sure, you know, like maybe none of those are good diagnostics, you know. Maybe what we know from classical thermodynamics isn't a good guideline here.
We have a question from Sayantan Ghosh.
Oh, okay, so I'll probably ask like a small question too. So first question is that is because you are using like a I mean Schwarzschild as well as De Sitter. So I'm asking that there are multiple horizons, right? As you said that one would be cosmological constant dominated and one would be Schwarzschild dominated. So I'm asking, so if there is also charge, let's say like I mean Riser Nostrum, I'm asking that in case there are say multiple roots of the f of x function, f of r function. So how do you know that which one is Cauchy surface? I mean, maybe in this case it doesn't matter because again you are comparing with the surface gravity. But I'm just wondering, like in general also, like for FR gravity, where sorry, if the metric is like FR dt square by 1 by FR dr square, and if there are multiple roots, would we always say that the closest to r equals to 0 is the Cauchy surface and rest of them? So that is one question. So could you just comment on that?
Let me address something about the inner horizon. So I did mention that there are three horizons, and the inner horizon is very important in this work in terms of that's what ensures that you have a non-zero minimal mass and that the temperature of the whole black hole surface gravity goes to 0 in a decorous way rather than going to infinity. So having the inner horizon there is very important to make this a nice, well-behaved thermodynamic system. Other than that, we have not incorporated the inner horizon into the analysis. And in particular, you might notice that I've talked about the total area as the sum of the black hole and cosmological areas. In terms of getting a better match between subsystems of spins and the black hole system, I think that the role of the inner horizon somehow has to be incorporated into the spin systems. You need something that imposes a non-zero minimal entropy at the small mass and also at the large mass end. Okay, so we had not figured out how to incorporate the important effects of the inner horizon. Now, there's just different ways that you could go. You could try to monkey with the spin system and say, well, you know, the spin system is so simple. You know, I think like the positive way to look at this is like, look how much agreement you get from just having n interacting fields in a background field. And the background field just is used to create a higher in energy, lower level. So it's really just counting. That's what's going on with the spins, it's just counting. And look how much is the same. But gee whiz, you have to add something else to get in some of the more complicated black hole physics. And playing with the system, my sense is that it's the inner horizon. On the other hand, you know, should the area of the inner horizon be included in the total area? Well, maybe, but there is a difference if you think of the space-time diagram that shows the three horizons, cosmological, black hole, and inner, that you can draw a space-like slice that intersects both the black hole and cosmological horizons. So you might think of that as, okay, all right, here's the entropy at this time on this space-like slice. There's no space-like slice you can draw that then also includes the inner horizon. So that was one reason for not including it. The other reason, of course, was that we had enough to analyze just with these two horizons. And it may be just because maybe connecting the horizons on a space like slice is not the right criterion. Maybe you get something even more interesting if you include the area of the inner horizon. So I don't know, but I think that's an interesting thing to explore.
And just a very short question. So what happens if the lambda is less than 0? Like, is the causal structure, I mean, is the question even makes sense? Because I mean, maybe the susceptibility is itself negative, because I'm not sure, because it would not like area would not even grow.
In anti-de Sitter, none of this structure happens. You don't have the cosmological horizon to start with. Okay.
Yes.
And the cosmological horizon is important in that it makes the system more like being in a box. The cosmological horizon makes the mass in a bounded range. Mass has a maximum and makes the entropy bounded. So those are big advantages, I think, conceptually of the cosmological system.
I see. So even the first picture you draw, that is the surface area versus the surface gravity, I mean, that would itself not make sense, right? I mean, mathematically.
Well, you don't have the cosmological horizon period.
Yes. So even that. Thank you very much, ma'am. Really great talk. Thank you.
Question by Neeraj Kumar.
Hello, am I audible? Hello.
Yes.
Hi.
Yeah. Okay. Thank you very much for a very nice talk. I really couldn't think any analogy of this N in black hole systems. I've been trying really hard, but this two-level system is really simple.
Yes.
I'm trying to think how we can extend it to maybe canonical ensemble. Can we think in like, okay, so can we incorporate something from Ising model that we have a spin system, and then we can tune the temperature somehow, or there is some interaction between the spins or something, just to go beyond microcanonical ensemble somehow.
Yeah, I think those are great questions. And again, the thing that I worked hard. I don't want to say I worked hard and got no result, but that's basically in terms of monkeying around and trying to find a way so that the entropy of the spin system, for example, started at a non-zero value. That's one of the differences, is that you have a non-zero area for the smallest mass black hole and non-zero area at the largest mass black hole. And so those correspond to, at least if with the correspondence areas entropy, to non-zero entropies. So how to incorporate that in the spin system, it is, so I don't know. I was looking for a picture plot to show you, like one of the things that you can do with the spin systems is that with the subsystem, we're able to get the temperatures to match, that at the larger energy end of the temperatures, instead of the spin system temperature going to 0, go to some non-zero negative value, so that it matches the kappa system curve for the black holes. So you put that in, you put it in, but getting the entropies to match, I couldn't figure. So I think it's a great question, and I think that to me, one of the fundamental questions was what corresponds to up or down. So what, again, to go rephrase what you said, very simple system. You have N, and you have a distinguishing between up and down, right? And so N, we can kind of think of, well, maybe finite mass or something. Up or down, like, so what's the analog of up or down? And my gut feeling, by gut, I mean after playing around with trying to make things match and stuff, thinking about this is, to me, I think that the best bet for up or down is that in the horizons, you can go in or out. And I don't mean that there's two horizons. I mean that each horizon you can, sorry, a generic place you can go in or out, but at a horizon it's kind of special. You can't go in or out. You can only go one way. So my guess is that the analog of up or down is kind of in or out, inward or outward for light rays. And then the light cones do something special at the black hole horizon and at the cosmological horizon. So the in and out becomes really fixed. You can only do one. But I don't know. I think that's the question.
We don't.
Okay, thank you so much.
If we don't have another question, then can I just mention when following up on Eleni's question, when you were discussing how it would change with Hawking radiation and so on. You showed this graph which reminded me a little bit of this famous page curve. Is that something that is connected in some sense to this scenario where you get some maximum amount of entropy and then it goes down? It's kind of the archetypical curve for unitary evaporation of black holes.
Yeah, so you're saying that the maximal entropy point is here, not the, I'm not sure if you can see my cursor.
Yeah, we can see it.
Okay. The maximal entropy point is kind of a mid-sized mass. It's not at the bottom of the, if you were thinking of a black hole evaporating, it's not at the bottom of that curve.
Yeah.
So maybe there's some other preferred state there. Hawking page, of course, is for negative lambda. And though that, I mean, there's a difference here, there actually are there are black hole states that exist there. And so maybe you're rephrasing it, so maybe there's something that's preferred. So I don't know. In the Hawking page transition with anti-de Sitter, there are no black hole states with like mass lower than, with temperature lower than a certain minimal temperature, a certain lowest temperature. Yeah. Yeah, so again, well, that's interesting because again, that's kind of in a canonical picture where you're thinking about changing the temperature. So I don't know. Yay, I don't know the answer to any of the questions so far.
Do we have any more questions?
Just to add maybe a little to that, yeah, I think Benito was thinking the dynamical evolution, right? So it's time would be on the x-axis, but I think that can correspond also to mass, right? So the mass that you have here like starts from a larger black hole and then it gets to zero. You would also have a peak. But I think there's another difference, and when you have Hawking radiation, you usually kind of consider also the entropy of the radiation itself and not just the horizon area. So yeah, I don't know if that would need to be taken into account then.
Yeah, well, that's an interesting point because if you start including that entropy is leaving the cosmological horizon, so we have to expand what we're counting. Yeah, and one might say, oh, it's just a small amount, but if it represents the entropy of the black hole, then eventually it's not small. Yeah.
Does it actually leave the horizon?
I'm sorry, I couldn't hear.
Yeah, I'm not entirely. I can't really picture if it does leave the cosmological horizon or not. And so, is that the case that it escapes the horizon? Because if it's very large and the horizon is receding.
Oh.
I'm not sure, I guess.
Well, no, you're right. So it's a question of ordering times. I mean, at first it's not, I mean, for any given packet of emitted radiation, it takes a certain amount of time for it to cross the cosmological horizon. Yeah. Yeah, so it depends upon, and especially if you're in the small mass regime, then the horizon's very far away. So, yeah. Yeah.
If there are no further questions, I think we've all been really stimulated by this talk. So
Well,
let's
thank you. Thank you very much.
begin.
All right. Well, I will say I found it very hard to talk without seeing the faces. So maybe I made the wrong choice in terms of having a big screen, but there you go. Yeah.
Okay.